Sir, video no sound.
Okay, I double check. Anyone know how to do with the sound? I'm checking on my side. Because actually using Zoom there, I know there is a setting that you can change the output to the PC sound. Or you can't. I think you cannot get the mic to respond, and then you got the feedback effect. Let me see. Sometimes what you see and what I see might be a little bit different because I'm using MacBook. Okay, never mind. I share the link for today because I can see that now how many is in, 117 is in. So that is just a revision, the video. So I will share the link, and then you can watch on your own, right? Because that's how is I'm thinking. I find the video. It's just that I'm thinking if we are waiting for others, then you can watch the video first. Oh, someone found already, yeah. Okay, so instead of that, we move to the lecture of today. So remember to get your attendance. So if halfway you have any issue on your internet and so on, you can always email me or send me the message through the Microsoft Teams. Right. So because the university now enforce on the real-time class, so you must join. Yeah. But if you have internet issue and so on, then actually you can watch the video after this, but then you have to notify me. If not, I will count you as an absent. So if you notify me, then I will count your attendance as a not count. Because now your attendance has three different category. The first one is attend, the second one is absent, and then the third one is not count. Right? So that's why you have to take note. Right? So you have to regularly check your attendance. If you found that there is any problems, so you have to contact your lecturers. Okay, because this trimester, by week 12, the university will generate the bar list. So if you don't have enough 80%, then you will be barred from exam. Okay, so maybe instead of we on the videos, so now we move to our slides here. Wait, where is my slide? Okay. Okay, I will turn off my video because last lectures I keep turning on my video. I found it's a bit lag or even on my side. Okay, so now you see my lecture, the lecture slide here. There's one of your friend actually asking me on this part. Okay, so he's asking why when we do the let me why when we differentiate this, okay, so we'll get two terms here. Okay, so there is a video. Watch. Yes, anyone?
Sir,
Yes.
and start the recording for this
Oh,
lecture.
sorry. Yeah.
Thank you.
Thank you for reminding. Thank you for reminding. Yeah. So it started. Okay. So since last lectures, after the last lecture, there is one of your friend actually asking me. The question is why when we differentiate the. Oh, sorry. Why when we differentiate the ER, right, differentiating the ER, then we will get the two components here, the ER and E theta, right? So I found a video. So I will share it in the link in the chat there, so you can have a look at it. Okay. So the video is over here. Copy. There you go. So you can watch this video to understand more. That is because when we differentiate the ER, there is an effect on the radial, the angular motion also, angular directions. Okay. Okay, then we'll move on. So this one we have gone through. Okay, I think we stop somewhere at the instantaneous center. So this is mainly again is a revision on your dynamics. So when I teach dynamics, I always find out that this instantaneous center of rotation is very easy to use as long as when you understand how it can be applied. So if you look at the slide here, so it says if the velocity have 2 points A and B are known, the instantaneous center of rotation lies on the intersection of the perpendiculars with the velocity vector through A and B. So what it means here is when we know the VA here and the VB here, so what you have to do is set the 90-degree and then you can just join the line. But because now this one already show you, so you know where to where it goes. That normally when you draw this line, you're drawing both sides long enough to find out where is the intersection. Okay? So once you find this intersection of the point C here, then that is your instantaneous center of rotation. So its name is called instantaneous center is because this point is keep changing. When the object is keep rotating, then this point it will be keep moving. So that's why it's called instantaneous only. So if the velocity vectors are parallel, the instantaneous center of rotation is at infinity and the angular velocity is 0. So what it means here is maybe let me clear it. So for example, now this is VA. So if my VB is parallel, right? So again, I draw a 90-degree. You will find out that these two lines will never meet, right? So that's why then you will not have instantaneous center. So this is also means that there is no angular motion for this object. So this object now will be purely translation. Right? There is no rotation actually happen. Okay? So the third sentence here, if the velocity vectors at A and B are perpendicular to the line AB, so the instantaneous center of rotation lies at the intersections of the line AB with the line joining the extremities of the velocity vector A and B. So it means that if both of them stay on the same line, like that, same line, so then you have to draw this vector correctly, scale, right? So if this is 5 meters per second, this is 3 meters per second, you have to draw the magnitude. Then you join this, you will still find the instantaneous center, okay? So if the velocity magnitude are equal, the instantaneous center of rotation is at infinity again. Means that if now the VA and VB is having the same, so again when you join, you will never meet. Okay, so that's why then again there's the angular velocity is 0. So for me this is very easy to use tools to find the relation between the velocity and the angular velocity of the system. So we look back at the two slider and the linkage, right? So we have point A here and point B here. So as we know, VA will only move in this direction, the horizontal directions. Okay, VA will only move the horizontal direction. VB is the vertical direction. So again, you set the perpendicular move, then you'll get this line and this line. So you'll find your instantaneous center at point C. Okay. So how do we how we calculate the rotational velocity here, right? Or angular velocity here. So what you need to do is you measure this. For example, now if we want to use the VA, so you just have to measure what is this radius, right? So here you call it AC, right? So that is why VA over AC, we will get the angular uh, velocity. Yeah. So once we get angular velocity, for example, in this case, we can also find what is BC. Okay. So when we know BC, we calculate the omega from VA, so we can easily find our VB, yeah, velocity at point B. Okay. So if you do some mathematics here on the linkage, the length here, the AC and BC, you will find out that VB is actually equal to VA tangent theta. Right. So similarly, you can use this instantaneous center on the gear movement. So this is a double gear row on the stationary lower rack. So this is a stationary lower rack. So the velocity of its center of the gear is 1.2 meters. So which is this one, 1.2 meters. So we want to determine the angular velocity of the gears, and then the velocity of the upper rack R, and the point D, yeah, the velocity at point D of the gear. So if you are trying to use the instantaneous center of rotation, so what we can do is we know VA is here, right? VB will be this point, right? And we also know that the VB can only move one direction, right? So now you connect the 90 degrees. That is where you find this point, the C, right? So once you get the C, you can find your VD. You just extend the line to the point D here, okay? And then you draw a 90 degree. Okay? So that will be your VD. So whether your VD is going to this facing up direction or facing down direction, that will depend on the direction of the angular velocity, the rotational direction. Right? So the simplest way is now we know that the VA is this direction. So is the instantaneous center is over here. So your rotational will be in the clockwise. Right? That's why your VD now will go this direction. Right? So similarly, your VB will go this direction. Right? It will not go the opposite direction. So they must follow. Right? So when we have this drawing, then we can start to do calculation as long as we know especially the radius. So VA is given 1.2 meter per second. So then you can measure the RA. Right? So the radius here, the R2 in this in this case is R1, 150 millimeters. So we can find the omega. So that's why the omega is VA over RA, which is 1.2 over 0.15, because it's 150 millimeters. So we will get the angular velocity is 8 radian per second. Okay. So then we will also from there, then we can find VB. Okay. Because VB is actually same as the VR, so that's why you get this relation here. So VB is RB omega, so that's why you will take R1 plus R2. So that's why you get 150 plus the 100 millimeters. So you get the 0.25 meters. So again, omega, you use back the 8 radian per second, because this is the instant, the rotational speed of the gears. So we can find the VR is 2 meters per second. So again, you find this is I. This is just to tell you where is the movement direction, where is the motion there. It's at the I direction, or which is, we call it x-axis. So this is written in the vector form. So normally in vector form, the x-axis, we are referring to I, vectors, or sometimes they draw like that. So y will be referring to j, and then z direction, normally they will refer to k vectors. So this is very common, commonly used vectors that to represent the x, y, and z axis, right? So now we can also find the VD there. Okay, so in order to find the VD, so the more important one is to find this RD, right? Because this is at the extremely end point here. So if you try, you basically based on the common sense, you will know that this is 45 degrees, because this is a circular object. So this will be 45 degrees. So we know that this part, or even this part, is actually the R1. So that's why we can take R1 and then square root of 2, multiply it. So we will get RD is 0.2121. So then we now multiply back again the 8 radian per second. We will get the RD value. It's not calculated, so we will get the RD value here, but at this direction, right? Since this is this side is 45, so that's why your VD will be 45 there. So basically, if you are trying to write that, you can say your VD is at the angle of 45 degrees. Okay, so you can always put this as a to let people know where is your position of your velocity. So then we will look at now we will look at another one, because previously we looked at the velocity. Okay, it is important to calculate the kinematics of the system, but for mechanics of machine, we are quite focused on the kinetic side. So that's why you will need acceleration value, because in order to find a force, if you are using the Newton's second law, basically you have to know the acceleration, right? Because F equal to ma under the Newton's second law. So now we will look at the absolute and relative acceleration in the plane motion. So again, when we have these objects, right, rigid body motion, or we call it plane motion, so then we can break it down again to two components here. So one is the translational. So now we assume that everything, we set A is a reference. So we have AA here, at point B as well, AA here. So how to cater the total motion here? So we have to include this rotational motion. So at the beginning of this lecture materials, basically, when we have pure rotation, this is what we call pure rotation, because now we assume that the point A is fixed, right? The point A is fixed here. So you'll have a tangential and the normal component, right? So that's why you have A tangential and A normal here. But if you look carefully, that here you will actually say ABA, because now we put A as the reference. So that's why we will say this is the acceleration at point B relative to point A. So B slash A, acceleration at point B relative to point A. So this the normal is facing into the center of rotation, but then the tangential is referring to the de-acceleration or the acceleration. Okay, so for example, now if this is the angular motion here, angular velocity here, if we have acceleration in the rotation, then our a tangential will be here. If we are de-acceleration, then we'll go the other side. Right? It will go this side. Okay. So it depends on either we are at the acceleration or de-acceleration. It's not whether we move clockwise or move counterclockwise. The right word we use is acceleration or de-acceleration. Right? So based on this, then we can write the formulas here. Right? Because A is a reference, so we will not focus on the A here. So we will focus on the AB. Okay? So AB is equal to AA plus ABA. So again, now ABA has break into two components. That's why we have a normal and the tangential component. So if you only look at the, or if you want to look at the polygon method, so we can draw the polygons here. So assuming that AA is to this direction, okay, so then AB is to this direction, sorry, this direction. So then in order to complete it, then we need these two components, the ABA normal and ABA tangential. So the angle here is follow. Okay, if this is the theta, so basically this is the theta. Okay, so that's how you get this angle. And then the normal and tangential is always separated by 90 degrees. Okay, so that is why you have this and this. So these two lines 90. So now if we assuming that the AA is to this direction, so again we can draw this. This is ABA normal. So again we are using this angle because of this, right? So again 90 degrees, right? We will go there, right? So that's why then it will equal to the AB. Okay, so there is different scenarios. So if we have AA here, so again this is normal. So the angle is again the theta. Then this is 90. So we can have A tangential. So by completing this polygon, we will get the AB. Yeah. So this is another example that you can look at. Okay. So once we draw this polygon, basically we can solve it using the two components here, the X and Y component. Okay. So now if you look at one of these example, or basically we will use this quite a lot in our mechanics of machine. So this is I will call this we will call this as 4-bar sliders. So basically remember that I will emphasize this again when we go into linkage. So the fixed ground is considered one of the link because the position from here to the slider is fixed. So that is why there is a link. Okay. Then there is a link 1, and then link 2 is this crank, link 3 is the connecting rod, and then link 4 is the piston, right? Because now there is a piston that it should contribute mass. When you have mass, then you will create under, if you look at the Newton's second law, then it will give us force. That's why we will consider the piston as an additional link as well. Okay. So if you look at here, so what you want to find here is AD. So we'll say AD is equal to AB plus ADB. Okay. So why basically the AB can be easily found if we know that there is what is the angular velocity of this one we call it link 2. Okay. This one I call it link 2. If you know it, the omega or the angular velocity of the link 2 and the acceleration of the link 2, so we can easily find where is the AB. So basically, again, if we know the omega and the alpha, which is the angular velocity and angular acceleration of the link 2, so basically you will have two components, the normal and the tangential component. So from there, actually we can calculate the AB. So that's why AB normally is become our reference, right? So then from here we just add in the ADB, right? So ADB again, you will have your tangential component is over here. So we do not know whether it's going which direction. It has to be up to the alpha here, right? So again, alpha, we do not know where are they going. So this is A, D, B, tangential. So again, we'll have A, D, B, normal for this component. Okay. So now, if we, but we know that the AD will go this direction, right, horizontal, because it's sliding only. Right, so we get this AD here. Right, so in this case, I believe that you will assume that the AB is without angular acceleration. So you still remember that the A normal is R omega square. A tangential is R alpha. So that if when our alpha is 0, then we will not have tangential component. So we only have this one. Okay? So that's why he can easily set this angle is 40 degree. Okay? So when there is no angular accelerations, you only have the normal component which go this direction. That's why your AB is at the 40 degrees to the direction. So then the AD is horizontal because this piston is only moving horizontal. So we got this line. But because we are finding the AD, we do not know where it will stop. We will just draw the line like this. But this one, then we can calculate the value. So we know that it should actually reach here by given a specific scale. So we depend on the scale we have. So ADB will just cross like that, right? So that from here, then we have to find what is the normal component and the tangential component for the ADB, okay? So the angle you have to calculate, right? Because we have this 40 degrees, the length, so we can calculate this. So they are basically two, let me see. So normally you'll be using, for example, if we have triangle like this, we have A, normally what we use. For example, this is theta, B, beta, C, alpha. Okay? So you have to remember these formulas. Sine theta is equal to B sine beta is equal to C sine alpha. This is one of it. This is sine formulas. So then the other one is C square is equal to A square plus B square minus 2 A B cos alpha. All right. So this is cosine function. So we will always use this. Right? So for example, just now this is link 2, this is link 3. So we get the beta. Okay. So what we have to do is we want to find the theta here. Okay, we want to find theta here. So we can use sine rules. So it means that the length of the link 3 divided by sine 40 degrees, and then the length of the link A divided by sine theta. So we can find what is the theta value. Okay. Okay. So that is how we find this value. One is find this value because this is 90 degrees, so this automatically same value. Okay. So because at this case, the link 2 is known, as I say, if we know the angular velocity and angular acceleration of the link 2, so basically that is known. And the P is just a slider, so it's also considered known in the directions. So that's why the bar that we will be investigating is actually the link 3 only. Okay. Okay, so now we move to the next. Okay, so another example here. This one we call it 4-bar linkage. So 4-bar. So again, the link from the point from here to here. This one we call it as a link 1. So we call it ground link or link 1. So we have again link 2, link 3. This is 2, 3, and 4. This is link 1. Okay, so we have 4-bar linkage in this case. Okay, so again, if we know the angular velocity and angular acceleration here, so again, I believe this this problem also the alpha is 0. So we only have omega. Okay, so then we can find out what is the velocity and so on at the point B here. Okay. So again, if since this bar 4 is again a pure rotational, so we will know that the velocity, okay, is either go this or this. So this is V B. Okay. So this is VD. So then if we know this, if we are looking at the velocity, so this is VB. Right, so again, the direction is based on the omega for velocity. So we can find the VD is equal to VB plus VDB. Yeah. So VB can be found using the omega of the link 2. Right. So we call it omega AB because this is point A to B. Yeah. So VAB multiply with the RB. So we get this value. So you can find out that actually this calculation they are using vectors. This is RB, this is RD and RDB. Yeah. Right. So this is the position of the bar. Right. So you just substitute here. Right. As a RB. So we will get it in terms of vectors. So as I mentioned now, this is a x-axis, this is a y-axis. So for VD that we have here, it is still the same thing, but the problem now is we do not know this omega dE. Alright, but RD we have here minus 17I plus 17J. So we have this. So but you also notice this RDB, sorry, this RD it actually measure from point E here. So that's why you have this 17, right? Minus 17 and positive 17, right? So this sometimes is a bit confused, right? So you have to be careful, right? But if you look at the RB, it's taken from point A here. So that's why it's positive 8 and positive 14, right? So that's why when we substitute, so we will get the VD in terms of omega DE. Yeah. So now if we move on to the VDB, okay. So we will this is VDB. So again, the RDB, if you look at it here, is the measurement, right, of point D relative to point B. Yeah. So now this RDB is measured from here. So that's why there is a positive 12 and positive 3 here. Okay. So you have to be careful. The reference point is different for all these R. So now we get this in terms of omega BD. Yeah? So then we can solve the X and the Y component because everything is in I and J, I and J, I and J. So we solve the I, solve the J. That means we substitute these three into the formulas. So then we can break it into two components here, X and Y. Right? So for extraction, it's still a very similar equation here. Right? So then we will have AD. Right? AD is R alpha plus R omega square. Right? So so R in this case is a RD, right? And then there's a sorry, just a moment. It calculated by right we should have get the omega DE and omega BD from here. This one we get, right? That's why then only we can continue, right? So omega DE, what we get is 11.29 K minus is okay, 11.229 K here. This is the omega DE from our velocity analysis. So then we put everything in, so you will get this component. So for AB, as I told you just now, that the alpha AB is assumed to be 0. That's why this component becomes 0. So we only have the omega AB is 20. And then the RB is again 8I plus 14J. So we will get this component. So omega BD from velocity analysis, we will get this value 29.33. Okay. So if we substitute everything in, so we get this part. So again, we have 1, 2, 3 here. So these 3 will all go back to these formulas. Again, we can solve the X and Y component. So basically, we'll solve the alpha BD and alpha DE here. Right? So this is angular extraction. Okay, we'll move on to the Newton's second Newton law of motions. So we have the 3 Newton's law, and that we keep on studying, right? As a mechanical engineer, we'll keep on touching on this. So the first one is a body at rest tends to remain at rest, and the body in motion at a constant velocity will tend to maintain its velocity unless acted upon an external force, right? So this one, we always say this is a static, right? This is a static condition where we say submission of force equal to 0. So this is Newton's first law. So Newton's second law. So we have when the time rate of change of momentum of a body is equal to the magnitude of the applied force and act in the direction of the force. The formulas we always see is summation of F equal to ma. Right? So this is Newton's second law. So the third one is for every action force, there is an equal and opposite reaction force. Right? So this is the third Newton law. Right? Every time when I see the third Newton's law, I always remember an advertisement from Adidas. Many years ago, I think it's about 12 years ago. Right? Adidas put out a very big notice board. That time I'm in Singapore. So it stated that the Adidas shoe is designed according to the Newton third law. Right? So if you want to look professional, next time you can tell people that the car tires is designed according to the Newton third law as well. Right? So that you don't want slips. So you always, whatever force that you apply, all right, so you wish that your reaction force is equal so that you won't waste any energy. Right? So remember your shoe, your new shoe, always fulfill this Newton third law until your shoe wear out. Right? So you slip and you fall down, then your shoe never follow Newton third law anymore. Right? That's why you have to change your shoe. Okay. So basically in mechanics of machine, we will use a lot on the Newton's second law. So the second law is expressed in terms of rate of change of momentum, or is mv, where m is the mass and v is the velocity. So the mass m is assumed to be constant. Right? So in this case, we always assume the mass is constant. The mass will not change. So that's why then the time rate of change of the mv is ma. So the F is the resultant of all force on the system acting on the mass center. So again, we have to focus on this so-called mass center. So there are a few keywords here. So first of it is mass is constant, right? And we are looking at the mass center, right, for Newton's second law. Okay, so now we look at the kinetic parts of it. Right? Equation of motion for a rigid body. So consider a rigid body acted upon by several external forces. So we have several external force. Assume that the body is made of a large number of particles. Right? Many points here. Right? Particles. For the motion of the mass center G of the body with respect to the Newtonian frame O, right? This is origin, right? So F equal to ma. We can use the Newton's second law. So for the motion of the body with respect to the centroidal frame G x prime, y prime, and z prime, which is this one. Okay, so we can write the angular moment. Right? So mg is equal to h dot g. So system of external force is equivalent to the system of the consisting of ma and hg. So we can look at the how we solve it, right? So angular momentum of the step may be computed by this formula given here. Okay, so if you are hardworking, then you can go and try to search more on the reading here. But basically, we will say that hg is equal to I omega. That's why after differentiating it, we will get h dot g. Right, so there is a dot there. So there is a rate of change of angular momentum is equal to I alpha. or I think the more frequent equation that you will see is we say torque is equal to I alpha. All right. So this one you will see this more instead of, because not much books or people will write it in terms of hg dot. You will see this, right? So results are also valid for plane motion of body which are symmetrical with respect to the reference point, plane. So results are not valid for asymmetrical bodies or three-dimensional motion. Right? So for our mechanics of machine, we still stick on the two dimensionals. Right? So we always assume that is symmetrical on to the reference plane. Right? So means if this is an object, so this how this object will look like at the three-dimensional space is you just extrude this. Okay? Mean at what level you cut at the z-axis, it will still look like this. Okay? So that's why when we say there is a potato is not very correct, because it should be same throughout the z-axis. Then only we call this symmetrical with respect to the reference plane. Okay, so to solve this rigid body motion, even though there is a 2-degree or two-dimensional problem, so we have to break it down into three components, which is the x, y, and the rotation. So we have you have the fx equal to max and the fy equal to may. So the next one is the mg equal to I alpha. Right? But normally I will call this as a torque or moment. Okay, moment. So I will not go into details. The D'Alembert principles basically is just an explanation over here. So we look at how we apply. Okay. So we have this here, okay, and you can see carefully that this is attached to a rope over here, and then you wrap it around. Okay. Similarly, like your yo-yo, the games that you play, the yo-yo. So you fix it, and then you have a cables. So what happens if once you pull this cable, what will happen? Okay. So the question here is a cord is wrapped around a homogeneous disc 15 kg. Okay. The cord is pulled outward with a force of 180 Newton. So what we have to find? We have to find the acceleration at the center of the disc in this point. The angular acceleration, which is alpha, and then the acceleration of the cord. Okay. So how we solve it? This is the data we have. Okay. So it's good that when you try to answer any questions, you can list down this first. Right. So to make sure that you at least you digest the questions properly, and then you draw this what I always call this free body diagrams. Right. So we draw the free body diagrams, and then expressing the external and effective force of the system. Right. So what is effective force at the x directions? Because if you look at here now, the things we only pull vertical with the T. So that's why there is no side force. So that's your external side force is 0. Then your this will have an initial of max, right? So because it's equal to 0, so your ax is 0. Now if you look at the y directions, okay, so you have a force T here going upward, but then you have the mass going down, the weight going down, which is the mg, so T minus W here, and then you have your inertia of this, so we have a MAY, okay? So that's why you can find your AY is T minus W over M. So the T given 180 Newton, W is mg, so you just multiply 15 kg with the g here, divided by the mass is 15 kg again. So you will get your AY is 2.19. So that's why when you write this equation, all this equation, you define this properly. Okay? So in this case, you divide to the right is positive, this one is upward is positive. That's why when we calculate it, we get a positive value. So it means that is upward. Okay? So if you set everything all this correctly, and then you get negative, it means that now your direction will go in the opposite direction. Right? Similar to this, the third equation here, right? So we have to set this, right? So this is these three things here is the normal direction we set to the right positive, going up positive, counterclockwise positive, right? So normally we set counterclockwise positive, not clockwise positive, right? So if you look at the moment, so again when we write this equation, so one thing you have to bear in your mind is the mg. This g is not simply put one, all right? So it's a reference. So moment at point G, right? That's why now you take the moment at point G, the W will not give you any effect. So the only effect you have is T multiplied with the R. Right? So that's why you get TR. So why is negative is because now if you stay at the point G here, you will find out that your T minus R will give you a clockwise motion. So that is negative. Right? So your inertia is I alpha. So we give I alpha there. So the I in this case is the mass moment of inertia. Okay? So I here is mass moment of inertia. That's why for this is a this. So it's half mr squared. The computer is a bit lag, right? So I is mr squared, so we get this, right? Multiply with alpha, so we can get alpha is negative 2t divided by mr. So when you calculate it, you will get your angular acceleration of the disc. So from here you calculate it, you get minus. So if you label your acceleration with these symbols, then you can remove the minus. Please remove the minus, okay? Because the minus has been representing by these symbols clockwise, right? If you don't put these symbols, then you can just maintain your minus. Because if any of the reader read your report, read your answer, because now if I see minus 48 radian per second, right, without any symbols there, then what I will do is I will refer back to your reference here. Right? So I see this positive counter is a counterclockwise. If you give me negative, mean it's a clockwise angular accelerations. Okay, then we can calculate the acceleration of the code. Okay, so again, ax is 0. Okay, if you look at the center of gravity there. Okay, that goes back. So AY is 2.19 going upward. Sorry. And then the alpha is 48 radian per second square clockwise. So we can find the acceleration of the code. So it basically is this point. So what is the acceleration at this point? Okay, so it will be, if you look at here now, if we take this as our reference, so that's why we have accelerations. Sorry, because there's a second. So what we do is we take this as a reference, so means that these things will move and then it will also turn. So there is a movement here. So that's why your A code is A plus A with respect to point G. So we have this A is 2.19 from here, the movement in the y direction, and then plus the angular effect, okay, or the rotational effect. So it's AG, okay. So the alpha here for this is 48 radian per second square. So we now multiply with the radius that we have. So it's 0.5 meters. Okay. So that's why we can find this A tangential, we call it. Okay. So that's why A tangential, the A tangential plus the A. Okay. So we will get the acceleration of the code. Okay. So it's 26.2 meter per second square going upward. Okay, just now the question is central rotation. If you look at here, means the things rotate at its center. So what happened now is the rotational is out of its center of gravity. Okay, no central rotation. Motion of a body is constrained to rotate about a fixed axis that does not pass through its mass center. So you look at the kinematic relation between the motion of the mass G and the motion of body about O. So we have A tangential is R alpha, A normal is R omega square, which is here. This one and this one. So now if you have this. So the kinematic relations are used to eliminate the A tangential and A normal from equation derived from D'Alembert principles or from the method of dynamic equilibrium. So what happened here is we can, instead of calculate, just now I already mentioned this is not simply right one. So now you can see the summation of moment at O, right? So it will calculate the moment at point O instead of G. So we will have I alpha because we have this the alpha here. So we have I alpha, and then there is another one is the. So if you look at here, the MA normal no effect because it's passing through the point O here. So we only have the MAT. So again, AT is R alpha. Right, so MAT is MR alpha multiplied with the radius here. So you have to find this radius. So we get the R here. Okay. So if we simplify this, then we'll get I plus MR square alpha. So then you will find out that this I plus MR square is actually the mass moment of inertia at the with respect to the point O, right? So every time you find the equation from your reference books or normally online, you find the mass moment of inertia I. That is always referring to IG. It refers to the center of gravity of the objects. Okay, so which is also here. So sometimes they will write IG here. Okay, but since now the rotation is not at the center of gravity, is actually out from the center of gravity at point O here. That's why if you want to simplify this formula in this way, you must find out what is IO first. Okay? If not, then you have to solve it this way if you are using uh, the IG. Okay, so you will have two components. One is the I alpha, the other one is MR alpha times R, or MAT times the R. So this is a force. This is a force multiplied with the radius. Okay, so if you look at the example here, we have two gears and bar here. So the portion AOB, where is AOB? AOB, yeah, of the mechanism is actuated by gear D. So this is a gear D. And at the instant shown has a clockwise angular velocity of 8 radian per second and a counterclockwise angular, this angular velocity at 8 radian per second and counterclockwise angular acceleration of 40 radian per second square. So we have to determine the tangential force exerted by gear D and the component of the reaction at the shaft O. So we have this information. ME, the gear E is 4 kg. KE here, this is the radius of gyration. Okay, this is the radius of gyration. That actually can be used to calculate the mass moment of inertia. Okay, and then MOB is 3 kg. The mass of the bar OB is 3 kg. Okay, so again, we started with the free body diagram. Please remember every time you solve the problem of mechanics problems, so draw the free body diagram, especially on your midterm or exam. Please draw it because this contribute to marks. Okay, I will give marks when you have free body diagrams. So then we compile what are the information we have. Okay, so counterclockwise angular acceleration 40 radian per second square, clockwise velocity at radian per second. So from here we can we find the weight. So just multiply the mass with the gravitational acceleration 9.81. So as I mentioned just now, the mass moment of inertia can be calculated whenever the radius of gyration is given. So means that the formula is I equal to mk square. So there is a mass moment of inertia. So that's why it gives us the ke. So we can square it and multiply with me in order to get the ie, right? The mass moment of inertia for the gear E. Okay. So if we multiply with the alpha given 40, okay, so we will get this 1.156 Newton meter. Okay. That's why just now I said T top is equal to I alpha. So you can see that the unit we get is Newton meter. Okay. So we are also given, or basically because we are given the alpha and the omega, so we can calculate the tangential, okay, and normal component. Okay, so here tangential component will be mr alpha. So mr is 0.2, right, which is here, right, multiply with the alpha is 40. Because what happened here is the gear E and the bar OB are moving together. They are moving as one part. So for normal component, MA normal. So M is 3 kg. R omega square, R is 0.2, omega is 8 radian per second square. Okay? So we will get these two components. Okay, so just now the K is only the given for the gear E. Yeah? So that's why for the bar OB, we still have to find is mass moment of inertia. So the IOB, it give us here is 1/12 ml square. This is for bar. Okay, the mass moment of inertia for bar. Okay, is half 1/12 ml square. So then multiply with the alpha. So that's why we get this 1.6 Newton meters. So now we can apply in our the three equation we have: summation of force at x, y, and the moment summation of moment equation. So now if you look at the summation of moment equations here, so we have a moment F equal to, because if you look at here, all these are passing through. All this is passing through the point O, so there is no effect. So that's why only the F here is effect. So the multiply the distance is the radius of the gear, 0.12 meters. Okay. So what are the inertia of this? So we have IE alpha, okay, which is over here. Then we have this component, okay, MOB, AOB tangential, okay, this one, multiply with the length here from this point to O, so it's 0.2. Oh, it's 0.2, which is this one, the length. And then also the I alpha, IOB alpha, which is this part. Okay. So from here we'll get the force 63 Newton. Okay. 63 Newton. Okay. So you will get basically you will get a positive value. Okay. That's why you know that the direction is going down. Right, the force. Because when force going down, it will give us the counterclockwise movement. So then we'll move on to the x component. Summation of force x equal to the right, is equal to the MA. Right? So again, we look at this part here. X direction. So anything on the x direction, only the reaction, the Rx, reaction force at the pin joint there, or the point O. So then on this side, we only have this component MOB, AOB tangential. So we find out that the reaction at the point O is 24 Newton, okay, to the right, because this is positive. Okay. So if you look at the vertical one, okay, so we have RY, okay, going up positive, F coming down negative, weight coming down, so we get the negative. Weight OB also coming down, so it's negative again. Okay. Then this side we only have this component, MOB, AOB, so it's going up, that's why it's positive. So we try to solve it, then we get the reaction RY is 24 Newton. Okay, this is also very important for mechanics of machine, mass moment of inertia and the center of gravity. So we'll go through. So when the mass of an object is distributed over some dimension, it will possess a moment with respect to any axis of the choice. So that's why you have to fix your rotational axis or the reference axis you want. Okay. Differential element of mass is also shown. So the mass moment or first moment of mass of the differential element is equal to the product of its mass and its distance for the axis of interest. Okay. So with respect to the XYZ axis, okay. So if you look at here, the moment of inertia of a plane area A about X and Y axis in its plane and about Z axis normal to its plane. So figure A can be defined as this. So means that if I trying to find the Ix, the mass moment of inertia with respect to the, sorry, this is the area moment with respect to this X, so we can use this formula. So if we choose Y, then we will use this. Okay? If we choose the Z axis, which is normal to our display here, then we will take this R as the distance. Okay. Okay, just how that one is, we come back to this. Just how this one is first moment. So now we come to the second moment. Okay. So if you look carefully, what is the difference? Yeah, back to that. First moment, we are looking at the area. So second moment, we are looking at the is mass. Right. So consider a body of mass m. So rotate about the axis OO. So this is the axis OO. So with angular accelerations of alpha. So an element of mass dm has a component of acceleration tangent to its circular path equal to r alpha. Okay, so that is why we get this. And the resultant tangential force on its element equal to r alpha dm. So the moment of this force about the axis OO is r square alpha, okay, dm, right? And the sum of the moment of this force of for all element is square root of integration of r square alpha dm. If you want to understand in detail, you can look at it. If not, you would use from the papers, from the textbook and so on. Okay, this is the explanation. Maybe I will skip this because by right you have been going through this. Scan the best moment of initial predefined geometries. For example, rectangular cylinders and so on. Okay, so the things become easy if we are given the radius of gyration, just now like the KE. Okay? If you are given the radius of gyration, then it will be easy for us to calculate its mass moment of inertia. So we just use these formulas, I equal to mk square. So the k is the radius of gyration. Okay. The other thing is just now we already look at it. Maybe we go back. Okay. Go to the wrong direction. Okay. Just a second, I'm have some technical issue here. Okay, we can go back, if not mistaken. Yeah, this is the one. That's how we see this. Okay, so if the rotation now is not at the center of gravity, that's why then we can do this. We can use this method. Right? This is developed from this. Right? So now if we come back to here, so we call it transfers of axis. That's why if you refer back just now, we will get this the mass moment of inertia. For example, this is the center of gravity, the G here. So now if I want to find the IO here, okay, so I can take the mass moment of inertia that we calculate at point G, right, which is the I dash here. Then we plus with the md square, right? Oh, where is the d? So maybe I draw another one. So if this is G, so we already calculated the IG here, right? So now my rotational axis I'm interested is I not here. So what I can do is I just find out what is this, right? And I know that this has a mass of m, so I can calculate my IO here. So it will be equal to IG plus md square. Okay, so this is how it works on this one, the transfers of axis. So if you do some calculation there, okay, you can also find the new so-called the new radius of gyration with respect to point O, okay, because what happened here is IG is m k, in this case you use the bar square plus md square. So my I naught now I can say this is mk square. That's why if I remove all the m, right, I will get this relation, right, which is this one. Okay, so you can also find the radius of gyration. Right? Can you see my PowerPoint now? Someone mentioned it's not changing. Okay, because my computer is a bit lag. Even I write, maybe after 3 seconds only it come out from my screen. Whatever I write. Oh. Okay, so this is the summary of it. Okay. So again, as I mentioned, we normally refer to the tables. Okay, unless you are calculating from a very basic part of it. because in mechanics of machine, we are more on the application of this mass moment of inertia. We are not learning what is mass moment of inertia, right? But for the revision side, so I have to highlight again or to refresh you about this mass moment of inertia that you have learned it before, right? So this is similar to the transfer axis. We call it parallel theorems. So I will skip it. So just now, if you see, I draw this, right? The IG, and then this is my IO here. So we have a D here. So the D, if you know the exact length, so you can use the D. If not, then you can use the Cartesian method. Because from here you see that I naught is IG plus MD squared. Right? So the D square can always, if we are in the XY plane, then it can always be X squared plus Y squared. Right? So it depends on which plane you are. So this one is at the YZ plane. Okay. Yeah. Okay. This one will be on the XZ plane. This one will be on the XY plane. Okay. So that's why if we have a 2 degree of freedom system, for example, this one, if I have X and Y here, right? So basically, the mass moment of inertia we are looking at is the Z-axis, because the rotation axis has to be normal to our screen now. Okay, so that's why you see XY plane. That's basically when we calculate the mass moment of inertia, is actually on the Z-axis. So what is the time now? Okay, so this one I already discussed just now. Similarly, okay. I think I don't want to spend too much time on this, touching all this derivation. Okay. So as I mentioned again, we are applying this. So what normally you do see is here. We use this, right? Instead of we go and calculate, right? We only use this. So for example, there is a rod or a bar. So we just find the Ix, right? The Iy and Iz is the same. So it's half ml square. So if you have a this, then the Ix, this is the Ix, means that now this have to rotate on the x-axis. So then we will use this. If the this is rotate at the y and the z-axis, so we have to use this formula, right? Similarly to the rectangle, so we have to be careful. So where is the x, where is the y? This is the x. So means your thing now rotate along the x-axis. Then it will be using these formulas. So please don't remember all these formula blindly. You must remember this formula with the diagram, right? Because I can put this plate on another plane, right? So if I rotate this plate to another plane, you still use all these Ix, Iy, and so on. You may get it wrong, all right? So this plate now, for example, this rectangular object now is lie on the YZ plane. That's why my Ix is this. If I lay this rectangular plate on the XZ plane, then all this will be have to be rearranged. So for example, now if I lay this plate on the XZ plane, this one instead of IX now it becomes IY. Yeah? Right? So you have to be very careful, okay? Because I think last year there are quite a number of students get it wrong. Because my formula sheet I give this, but my question I put my rectangular plate on the YZ plane. So then they get it wrong. Okay. Let me see how many slides this will go. Again, we will try to finish this sample problem 10, and then we will end our class today. Okay. So because this one will be related to the experiment 4, the mass moment of inertia, that we will start on next week. Yeah, so I better cover this. So steel forging consists of 150 by 150, 150 by 50 and 50 rectangular prism. So this is the center part here, 50 by 50 multiplied with 150, the height. And 2 cylinders, diameters 50. So that's why he gives it 25 is the radius. The diameter is 50. Right? And the length 75. Right? This means the moment of inertia of the forging with respect to the coordinate axis, knowing that the density of the steel is 7,850 kilogram per meter cube. So for the prism here, the center part here, the volume is just multiply the 3 axis of it, 3 dimension of it, 50 mm multiply with 50 mm multiply with 150 mm. So you get 3.75 multiply with the, this one is m. This one is m. Oh, come right. M equal to rho V. Yeah? So this density multiplied with the volume. Okay? So we get 2.94. So for cylinders, we calculate each of it. So it's pi r square times t, yeah, the height. Okay? If you still remember, pi r square multiplied with t, that is the volume for cylinders. So you calculated the area multiplied with the thickness. Okay? And then again, this is V, this is rho. So rho V, we get 1.5156. So this one, we calculated the moment of inertia. So this is 1 over 12 m. We back to the this one. So when we have cylinders, when we have this one, okay, so we are using this is a prism. So that's why we have a b square and a c square. So for example, now this is ix, this direction. So you'll find that we'll take b square and c square. So you look at here. So we will take ix. So let us look at it. So this is x. This is z. So if you look from the x plane, this length and this length is same as when we look at this plane. We have this length and this length is the same. Okay? That's why the calculation here, ix and iz is the same. Okay? When we go to iy, because now we have to look from here, so we will take this length and this length square. Okay? That's why you find out that your iy is a different value. Okay. So again, for cylinders, okay, so we have okay, so if you look at that, the Iz and Iz, if we refer to its center of gravity, it will be same. Okay, so Ix will be using this, but then you will see this part. Okay, this is an additional one. Okay, this is the parallel theorem. Okay, so now Ix half ma square. So we go back here. So for example, this is the x-axis. So means that if I find the Ix through its center of gravity, okay, so we will be using this formula half ma square. But the problem is this axis and this axis has a distance of 50 millimeter. So same as this. This is also 50 millimeters. Okay, so that's why he only do one time. Okay, so that's why you have to have my square. Okay, so my square 50 millimeters. Okay, so that's why when we find this is Ix at the global axis x here, not the center of gravity. Okay, same for that when we do the Iy, so we have to find Ig here. Ig, maybe I call it I. Just a second. Igy. Okay, so we can use the formula, but then we have to find how far this to this. Okay, that's why we get the Iy, and then we have to find how far it is the mx. Okay, so that's why we take the 62.5. Okay, there is a distance. Okay, because you have to move. This is half of this one is 25. Okay, from the axis to the side here is 25. From this side here to the center of gravity here is another 37.5. So 37.5 plus 25, you get the 60. What is the value? 62.5. Okay. So for Iz will be much more complicated. Okay. Because if you look at here, Iz is here. Now you have to move to this. So you have to find this distance. So or when I draw two view, the side view, this is your axis of the Z. This is your central gravity of your cylinders. So that's why you have to find this x value and this y value. And then you square. Then you'll find this is your distance. Okay, distance square. That's why your d square is x square plus y square. So similarly to the bottom here, right, is the same value. Right? That's why you find this x square plus y square over here. This is the one. So you'll find the Iz. So from here you can find your mass moment of inertia at x, y, and z for these objects. Okay. So the important or the application of why we need this, one of the application of why we need to find this mass moment of inertia. So for example, now this is the object, and I have to install a motor here to rotate. Right, this is a motor to rotate this part at the x-axis. Then is good that I know my Ix, right? So then you can calculate what is your torque required by your model in order to turn these parts at the x-axis. Okay. So this is a calculation. Okay. Where is it? 3 point. 251. Wait. Oh, then you have to add in all the three, okay? Three components. Ix, Iy, and Iz, okay? That's why you have to take the prism, multiply, this is the prism, only one part, this is the cylinders, then you have to times 2, right? Because you have 2 cylinders, okay? So same for all the 3. So this is your final answer. So we'll do this on experiment 4, right? So I think today is long enough, okay? So any questions? Or are you guys still awake over on your PC or your handphone? Okay, if no, or you can go through the slide again. If you have any question, you can always send me and ask me. I may not respond immediately. I will try to respond before the next class, right? And I think if the question is a good question, then I will share to everyone again. Like today, I share to you the student asking why when we do the DER over DT, then why we get the theta dot D theta over theta dot and the E theta, okay? So that is what happened. Before we end, I share you another link. So if you have time, you can watch on the velocity and acceleration in the translation and rotation frame. So you can watch this. It's a video from MIT. It's presented by the Professor J. Kim Van Diever. Is one of the very well-known dynamics professors in the world, right? Because he's the one who developed the vortex-induced vibration simulation for all the offshore oil and gas industry. So he's a very great professor, right, in the industries. Okay, if not, then I will end the class today. So please make sure you have take your attendance. Let me check how many attendance I have now. 1, 2, 4. I think there is someone missing. So you have to scroll all the way up to your chat room there. You scroll up and then you have to click the attend and then submit your vote. Right? So I only got 1, 2, 6 up to now. But I look at my attendance participant list, I have 134. But in my timetable, I have 138 students. Please make sure you take your attendance. Okay, I think thank you very much and see you on